So the fourth problem, count number of balanced permutations from the last weekly contest. We give a number in terms of a string in which each character is just a digit from 0 to 9, and we are asked to find distinct permutations of num such that each permutation are balanced. By balanced, we mean that, for example, 132 is one permutation of 123, and this here the odd indices sum, that is 3, and the even indices sum, that is 1 and 2, both sum up to 3. Since they are equal, that's why they are balanced. So we want all the distinct permutations that is there. So, well, the first brute force approach that comes to our mind is, why don't we generate all the permutations if that's possible, right? That will take a time complexity of n factorial, because we have, suppose there is three characters, then six total permutations, that is 3 factorial, and if in general that will be n factorial. And in every permutation we also need to do a O of n check to find if it's balanced or not, right? So it's going to be n factorial into n, which is not going to pass, irrespective of how small the constraints are. So we need to optimize this heavy thing that we have right here. Do we even need to generate uh, all the permutations? That's the first question. And how can we optimize it, right? So firstly, in the question it's given that we have only 0 to 9, right? That's what the numbers are. So we have a finite selection that we need to do in our combination, right? So if I have, suppose, a frequency map 6, 7, 8, 9, and suppose there are 2 zeros, 4 ones, 8 twos, 3 sixes, 4 3 fours, 1 5, 7 0 0 2. Alright, suppose this is what I have, and I want to find all the permutation using these digits in the within the frequency bounds, so that I exhaust all the frequency and eventually get the answer, right? So firstly, if I want to divide it into odd and even indices, if I think in that way, then eventually what will be the size of the odd set or container or whatever, and what will be the size of even set? The size will be equal, right? In most cases, or in some cases, it might be equal. In other cases, even might be one larger, right? Because suppose this, suppose I had 0, 1, 2, 3, right? So in this case, I have two even indices and two odd indices, they are equal. And if I have one more, then I have one extra even indices, and that's the only possibility, the only two possibility that is there. So the size here can be n by 2, and here it can be n plus 1 by 2, right? So this is going to be the size. What is going to be the sum then? Well, that is pretty easy. The total sum of the numbers or number string divided by 2 will be the individual sums of the two sets. And since we are considering it or wanting it to be balanced, there should be this should be the target for each set, right? So sum for odd set should be target, sum for even set should be target. So these are the three things that we need to take care of. Now comes the part where we need to do the permutation, right? Well, so firstly we need to exhaust all the elements because this is the size that we want. So I can iterate through every number in a DP way, right? I can do a DP approach of iterating through every number. I can have this frequency stored from num and use it to iterate. And every time I iterate for on a number, then if I can choose, right? I can choose few elements in the odd set and the remaining will go to the even set because I want to exhaust everything, right? So that's the first thing. The second thing is there can be two permutations, right? So if I have this and so on as the odd set, and similarly this as the even set, then if the two numbers are different, then among the odd set itself, I can have few permutations. Similarly, for the distinct numbers, I can have a permutation within the even set also, and then finally, uh, I can use or multiply both the permutation of the odd set and the even set to get the total number of ways that is possible, right? Now comes the part where how I will calculate the permutation. Well, if I have 1, 2, 3, 4, 5, suppose, if I have this, then what's going to be the permutation? It's going to be 5 factorial, right? And what if I had 1, 1, 2, 2, and 3, 4, 5, right? In that case, it should be 1, 2, 3, 4, 5, 6, 7 factorial divide by what? Divide by the common numbers or the common count that I have. So that will be 2 factorial and 2 factorial. So 2 factorial into 2 factorial, right? This will be the total number of ways to permute this particular combination. Similar thing goes for this one as well. And this is a famous formula in permutations that we can use here, and we are going to use this in this problem. Well, now how will we calculate this? This is easy. The factorials are easy. 7 factorial, 2 factorial, 2 factorial can be calculated if we are, wise about it, then we can just store, since there are only 80 numbers, we can just store the number, or actually this is basically this particular number or digit 7 is what? It's the count of the total number of elements, right? So the count of the total number of elements can vary from 1 to the length of this particular number. So I can just calculate for each of that number. I can calculate its factorial and store it, pre-compute it and store it, right? So that's done. So if I have the factorial stored, then the next thing comes is, let me also write the thing. Let's pre-compute and store the factorials. The next thing comes is this formula that we need to compute. So that's nothing but n factorial divided by a factorial into b factorial and so on and so forth. How to calculate this? Well, there is this theorem that we should know before solving this problem. Then that is basically this. If I have a prime number that I am modding it with, then this says that it is equal to or equivalent to I to the power mod minus 2. So I'm not going to prove this. This is a well-known theorem, and before solving this problem, we need to know, otherwise we can't solve this problem, right? So this is the theorem that we are going to use. Well, how is it going to help me? Since I would already know the value of a factorial and b factorial, right? So I can use that to get the denominator, the total denominator that there is, right? And use that in place of I to find the value using this formula, and then basically multiply it with this particular value that I can still get it from the pre-computed values in O of 1, right? So this will be easy enough. O of 1. And now comes the part where how are we going to find this value, because we are going to do this inside our dp function, right? Then how are we going to get the values? Well, as I iterate or as I go down, the stack function inside dp, in every stack call, I will be choosing a particular value, right? I'll be choosing the value. I'll choose suppose 0. I'll choose two zeros in odd set and zero zeros in even set, right? Then what I'm essentially doing is calculating. Let me write it like this: while inside dp, for every call, I will compute the permutation of odd set and even set, and that I am going to do in this way. For every call, I will select a number. I will select the few numbers for the odd set, and the remaining will already automatically go to the even set, right? Select few numbers, few count of the numbers in odd set, remaining will go in even set. And this particular count value denotes what? It denotes this particular A or B or C, whatever, right? That's what it denotes, because I am having zeros two times. So I am going to divide it by 2 factorial. So I can use that value from the pre-computed factorials and get the denominator and prepare the denominator as I go inside every DP call, right? So essentially what I'll get is a factorial, and I'll also get b factorial for the even set as well. So I'll keep finding my denominator as I go forward. and at the end, I will need the numerator, right? So let me write denominator. I don't know the spelling. Denominator is all set. In the base case, now we will reach the base case, right? Base case will be what? Uh, Base case will be when the odd size or the even size, whichever I am, using as a state. I don't need both the sizes to be the state of the DP function, right? I can just use odd size as a state and use that inside my base case to be equal to n by 2, because that's what we had told when we were told that n by 2 is going to be the odd size set at the end. Okay, so if this is equal to n by 2 and uh, the sum, so we'll also have a state called sum or the current sum, which should be equal to the target, right? If that is the case, then I am going to uh, return the numerator, right? I have the denominator all set. What's going to be the numerator? Well, that's pretty simple. It's always going to be n by 2 factorial into n plus 1 by 2 factorial, right? Because this particular set's numerator will be n by 2 factorial and this particular set's numerator will be n plus 1 by 2 factorial, and the total combined numerator will be the multiplication of both. So n by 2 factorial into n plus 1 by 2 factorial, right? So this is going to be the base case. Else, if that is not the case, by the way, this should all be within a condition that I have reached number as 10, right? So essentially, I am iterating over inside my DP, I'm iterating over, the number that is going to vary from 0 to 9. So if my number is 10, that means I've reached the base case. Inside that, I'm going to check this, and based on that, I'll return this or I'll return 0. So this whole thing will be inside if number, let me call this number is equal to 10. It otherwise return 0. So that's it. Let's solve this. Uh, Last thing, I think I forgot to tell that since I am going to store the factorials, right? Why not store the inverse factorials of that number as well? So if I am storing factorial a factorial, then I'll also store its inverse factorial as I go, so that it's basically of one operation inside D, right? And the last thing is, what is this value? Since I am going to calculate this value, I can use binary exponentiation and do the granular moduling as I do that exponentiation and get the value eventually. So let's write that first, or let's so I need a frequency, right? I am going to declare it outside so that I don't need to pass it to the DP function. So my frequency will be frequency, my pre-computed value will be factorial, and my another pre-computed value will be inverse factorial. frequency dot size will be, or resize will be of 10, since there are going to be 0 to 9 as digits. Factorial dot resize is going to be the number of characters that there is. So let me also get that value inside n. I'm going to declare it outside so that I can reuse it inside my DP function. And here the size resize will be n plus 1, so that we include the n value as well. Initially the value will be 1 because we are going to multiply it, right? So we need initial value to be 1. Otherwise, if we have 0, then all the values will be 0. Inverse factorial again will be the same thing. So alright, I will have a sum. So sum will be 0 initially. I'll iterate, and since this is a character and num is a string, so I will get the sum of every element inside num. So that will be n minus 0, and I'll also update the frequency. So frequency of num minus 0 will be incremented. At this point, since this is a base case or edge case, if the total sum that is stored in sum, if it is not divisible by 2, then there is 0 ways that we can divide the set or the number. Then sum mod 2, if it is equal to 1, in that case return 0 right here. Otherwise uh, otherwise get the target. What is going to be the target? Let me declare it here. Target is going to be sum by 2. Alright, and let's compute the factorials now for all the numbers within 1 till the total size of num, that is I is less than equal to n. Get the factorials and store it inside this fact vector. So for this particular value, I is equal to 1, what is going to be its factorial? Well, it's going to be I into factorial of I minus 1, right? So fact of I is equal to I into fact of I minus 1. And each time I do that, I will also have a mod. Finally, I will also iterate or calculate the value for I, and that value will be inverse factorial. I'm going to use the theorem, that is this one. So I'm going to calculate this, right? I in to the power mod minus 2. So let me declare the mod here. And its value is going to be 1 divided by, sorry, so it's going to be I to the power mod minus 2, right? So I'm going to use binary exponentiation and pass I and mod minus 2 to it as base and exponent, and do the rest and return the value here. So binary expo base will be I, exponent power will be mod minus 2, and right here It's going to be long binary expo. The base will be base, first argument, second will be exponent. I will get the result and initialize it with 1, while exponent or expo is greater than 0. Keep going. If exponent is mod 2 is equal to 1, so it's not divisible by 2. That means I can just use one base and update the result, multiply it with result, right? So I can do a base into result, and at this point my exponent or xp is going to be used by 1, right? Because I multiplied base once, and as I go I'll also do mod, because that's the whole point. Now the exponent will get reduced by 1. Now exponent will always be divisible by 2 at this point outside the if condition. So I'll do a base is equal to base into base. So I'm now squaring it, right? So I'm essentially dividing exponent, reducing exponent by 2. I'll keep modding as I go. Exponent will be divided by 2, and I'm going to return result here. Right, so this is the binary exponentiation. It's going to return me the value that I require here. Let me do a mod here as well. Right, this can be very big as a value, so let me multiply it by long, and that's it. At this point I'm good to call the dp function, right? How many states do I require? The first state will be the number that I am at, 0, 1, 2, whatever. Second state will be the size that I'm keeping track of. I will choose odd size. You can also choose even size to keep track of. We don't need both as a state. We don't need that much overhead. The third thing is current sum. So 3 sets or 3 states. That's what we need. Return, solve, return, solve. The first state will be 0, since I'll start from number 0. Second state will be the count, uh, or the size, odd size, right? Number of elements that are chosen for the odd set. So I'll call it, that will be 0 initially. And last thing is sum, that will also be 0 initially. So let me just write it number. The second thing is odd size. The third thing is current sum. So this is going to return integer, the total number of ways, and the first argument will be the number, second argument will be the odd size, third argument will be current sum. So the base case, as we talked about it, base case will be if number at this point is 10, which I don't even require, right? I have everything that I need. I have gone through all the numbers that I can. That means it's time to tell the number of ways, right? Or get the numerator. So if num is equal to 10, then check if the odd size is equal to n by 2, and since n I have declared it outside, so I can access it here. We can also create a lambda function if that's the case, and sorry, n by 2 and current sum is equal to target, which is sum by 2. If that is the case, then return permutation of the numerator, and that's going to be odd size factorial, fact of odd size and even size. So let me also create a even size variable. That's going to be n minus odd size, right? All right. So this is going to be our value. Let me also mod it, and let me also multiply it by long so that I don't have to worry about overflow. Else return 0 because there's no point in moving forward. Now I am at a number and I want to divide its frequency count into two sets, right? So I will traverse through its different frequency count that I can take for a set, right? So I is equal to from 0 till what value? Well, till suppose I am at 2, I can move from 0 till 8. But uh, what if I've already exhausted? At this point, I've already exhausted or reached the point where the even set size or the odd set size is already over the limit, right? I've chosen more than the required elements. In that case, that's not required, right? So either I should be less than I mean the minimum of the two, right? I should select either the frequency limit for num, or I should select the remaining number of odd size. So since I'm keeping track of the odd size, I'm trying to find the odd size count. I can even call this instead of I can call this odd count. So this will be the remaining odd count that we can have, and that is odd size total size minus odd size. So this n by 2 will be the total size of odd set, and minus odd size will be the maximum odd count that I can take from this particular number's frequency. Alright. Finally, I will increase the odd count, and at this point I must also have an answer declared here, which I can increment. So right here I need the expression or the recurrence relation, and that's going to be the denominators, right? So I want the denominators, which is nothing but the inverse function of the odd count and the even count, right? So if this is the odd count and this is the even count, then I am going to multiply it, correct? So essentially what I'm doing is I am calculating the even count here. I already have the odd count here. I can use that to find the uh, odd count. So odd count will be the total frequency number that there is minus odd count. So for this particular number, For the odd set, I will have odd count. For the even set, I will have even count. And I'm going to multiply I factorial of odd count into I factorial of even count. And I'm going to call the recurrence relation, that is the solve function for the next number. Now my odd size will be odd size plus the odd count. Right, that's what I have increased the odd set by, and the current sum will be incremented by the odd count multiplied by the number or the value, right? And that is number, and that's what our recurrence relation will be. Let's be careful and keep modding it as I go. So this is the first mod, and let's keep it inside a bracket. This is the second mod for the solve function, and this is the total mod for the entire increment, right? And now we are good to return the answer. And let's hope for the best if it works, or if there are silly mistakes. We need to memorize it. Okay, so this should be n. By the way, I'm already using n here, so instead let's take character. Okay, this should be I fact. So this is failing at this point. Alright, so let me add one error here. Okay, there is still some issues. Factorial of I factorial of I will be my bad. So I made a mistake here. So this should be I factorial to the power the exponent mod minus 2, right? And I factorial I would have calculated already here by the time I reach here. So I can use that value factorial of I, and that will do the binary exponentiation and give me the I factorial value. And yeah, I think let's see it now. Okay, now let's memorize it. Since we have three states, we will need a 3D DT. Let me declare it outside the main function. Vector of int dash. Right here, I will resize it. The first argument that I'm passing, the first state will be number, and that is varying from 0 to 9. So 10 vector of int. All right. This is varying. This is odd size, so it's varying from 0 till n by 2, right? 0 till n by 2. So I will take n by 2 plus 1, and the next thing is the current sum which is essentially, which will be basically varying from 0 till the target value. So I'll be cautious and check if current sum is greater than target and at any point. In that case, return 0 here, and this will be of size target plus 1, comma initial value will be minus 1, and that's it. So at this point, if cache of cache of num odd size and current sum, if it is not equal to minus 1, in that case return the cache value and initialize it here, and let's see if this works. Alright, this does work. Time complexity will be, since we have three states and one state is O of 10, right? The other state is going from, it has an n value, so O of n, and this is also varying from, in worst case it will be O of n. So overall we see as O of n square, but that is not the case because for every DP call we also do uh, frequency, iteration over the frequency as well, and for each digit the frequency in worst case can be O of n as well. So in total I think the time complexity will be O of n cube, and space complexity will be O of n square, because 10 is just constant, so cache will be O of n square. Other things will be smaller in size than cache, so this will be the dominating one, and that's the whole problem. Thanks.